Okay, picking up where we left off, limits, page 4. The last thing we had was these limits that I asked you to try algebraically, and I gave you a hint about how to do them. And I'm trying to erase a little dot that was bugging me. And so here's what they are. So the first one, when you see radicals, if you plug in, you get 0 over 0. You know you're supposed to do algebra. Then a common trick is to use the conjugate in order to simplify it and turn it into something where you can plug that value in. So I multiplied top and bottom by square root of x plus 2 instead. That's a conjugate. And I FOILed the top, but I didn't FOIL the bottom because the whole point, the whole problem with this one is this x minus 4 that's in the bottom. That's the issue, because that's what's keeping me from plugging 4 in. So what I want to do is I want to cancel that thing out if I can. And so I don't want to FOIL it, because multiply the denominator, those two binomials together, because if I do that, it's just going to be harder to figure out how to get rid of it. And so I didn't FOIL the bottom because I'm trying to cancel out the x minus 4, not hide it by FOILing it. So the nice thing is that the numerator, when you multiplied it out, it worked. It gave you an x minus 4 on the top. So that cancels out with this x minus 4. And now you can plug in 4. You plug in 4 and you get the answer. So that's the idea of multiplying by the conjugate to cancel out that denominator factor that's causing you problems. The second one over here was the fraction one. This is a little trickier because there's two variables. So h and x are not related to each other. And so as a result, as h goes to 0, x could be doing anything. And so x isn't going to go away. This is not going to have a number for an answer. And so we just have to work it out, and our answer involves x. Muscle car out the window. And so, not mine. So now let's see how we work this out. In the numerator, I got a common denominator in the numerator, so I could turn it into one fraction. And so I turned it into one fraction. One thing to notice here is this minus h. That's a really common mistake, because you're subtracting this whole expression. You have to distribute that negative and subtract both the x and the h in that numerator. In the numerator of the numerator. Yeah. And so that numerator becomes this expression right here. And then I did the flippy trick, multiplied by the reciprocal. And so that's the 1 over h there. And then things start canceling. You know, the x's cancel out, x minus x, those can go away. And then I've just got a negative h in the numerator and an h in the denominator. So I can cancel those out and leave a negative 1. Remember, you can't cancel that h out until it's by itself, because if it's adding or subtracting onto anything, you can't cancel it. But because it's multiplying, well, it's by itself, then that'd be fine. And so they cancel out, you get negative 1 in the numerator, and at that point, the h in the denominator, again, that's my problem thing, is that h in the denominator. This h right here is why I can't plug in 0. So I'm trying to cancel that out, because once it's gone, then I can plug in 0. And then I get to this expression right here, and now the h can become 0. This is about as hard as the algebra gets this year, I'll be honest with you. Like, the algebra is not, I mean, we're going to see different kinds of expressions, but the algebra doesn't get, like, it's not, calculus isn't just super duper algebra or something. It's using our algebra that we've learned before in doing new things. So, anyway, be happy. Next page. Moving on. Computer's a little slow today. Earlier I talked about when would plugging in not work. And so I just want to address that really quickly, because I said if you can plug it in and get an answer, then that's usually the limit. And the only way it could be different is if you plug in and you get an answer, but for some reason what happens right there is different than what happens immediately next to it. So these are two examples. The limit as x approaches 0 of square root of x, the answer is that the limit does not exist. DNE is an accepted abbreviation that a lot of teachers use, so it'll be fine. And the reason why is because you can't approach it from the left-hand side. Remember, we have to have, as you're approaching from the right and as you're approaching from the left, you're approaching the same thing, and we don't have that here. So technically, the limit doesn't exist. You might wonder, well, could we approach from one side and just do this side? Stay tuned, that's coming. Next one is a piecewise function. You should be comfortable with these. X squared if x is less than 0, and then x plus 1 if x is greater than or equal to 0. So you have these two branches together making the one function. It's just one function, but with two different formulas, depending on where you are. And again, the limit does not exist here because we're approaching 0. And as you approach 0, you're approaching 0 on one side and 1 on the other side. Notice if it wasn't approaching 0, then you would be fine. Like if I was x approaching 2, well, as I get closer and closer to 2, there's a y value I'm getting closer and closer to. It's 3. And so that would be fine. It's just that we're happening to approach the thing where there's the break. And it's defined in one spot, but not the other. There's a few limits that you just need to know. If you substitute, they're just indeterminate, 0 or 0. And so you could create a table of values and try it yourself. On this one, you'd plug in x equal to 0.1 and then 0.01 and 0.001 and plug it into this expression. You'll find you get an answer closer and closer to 1. But that's also true if you plug in negative 0.1 and negative 0.01 and negative 0.001. Remember, we have to get the same thing from both sides. And that's also true for sine x over x. That one's also equal to 1. But this one turns out to be 0 instead. This is why 0 over 0 is indeterminate. When you have 0 over 0, you don't know what's happening, because what's happening in the middle one is that they're both getting infinitely small, but the numerator is getting smaller so much faster than the denominator that the ratio is getting closer and closer to 0. Like the numerator's at 0.01 when the denominator is just at, like 0.1. or something. And it gets even worse as you get closer and closer to 0. So that's the issue with that one. So that one's 0, and you can see why we call these things indeterminate, because you don't know. Quick summary of what you should be able to do so far. Understand a limit expression, understand what that means. Maybe you're still a little confused about why we're doing this, and that's really going to get answered. I gave you that y-intercept example, but there's going to be a lot more, and you'll be like, oh, okay, I get why they use limits. You should know when a limit exists and when it doesn't. You should be able to find limits using a graph or table. I give you a calculator. I give you some weird expression that you have to find the limit for, and you should be able to approximate it by just kind of plugging in numbers. And then algebraically find a limit using any of those techniques that we mentioned before. Okay, now we just have to go to a couple more complicated limits. So we're going to look at these two here. So in these ones, x is approaching 0. It's indeterminate both times. So it's like, what do I do? One thing you can do is you can do a thing I call bite-sized chunks. I'm trying to speed up a little bit because I think I have just enough time. You can, if you can separate the fractions or separate the expression out into a bunch of pieces, and each little one has a limit, then you can use the bite-sized pieces instead of doing the whole thing. So in this case, x is approaching 0. This has a limit. This one approaches 1. And this has a limit because this is, well, infinitely close to 1/2. So the answer is just 1/2. So bite-sized chunks, I can break it up into pieces as long as I can find all the limits for all the little pieces. The second one looks really similar, but the problem is it's not as easy to just move the two. You can't just like pull the 2 out in front or something with a sign there. And so it's like, oh, what am I going to do now? I introduced this one because I wanted to remind you of your trig identities, and you can see where this is so helpful. So pause it right now, and I want you to break this up into bite-sized chunks and see if you get the correct answer. So pause me and break it up into bite-sized chunks and see what you think the limit is. Okay, and here you go. Give it to you here. I did sine x over x, and then 2 cosine x over 1. You could have broken it up into 3 chunks. That would be fine. This one approaches 1. This one approaches 2, because cosine of 0 is 1. So you can plug in 0 into that one. And so you get an answer of 2. Finally, not finally, almost finally, I've got this one. Now this one's tougher because we don't have, x is approaching 1, not 0. And we've got sine of x minus 1. What am I supposed to do with that? So what we're going to do is we're going to do a little substitution here. There'd be a couple different ways you could do this one, but this is the way I want to do it. And it kind of is a sneak preview for stuff later. So we're going to turn all x minus 1 into u. And so this thing now becomes a limit. I'm not going to write anything down there yet, of the sine of u. And now I want to turn this and this into u stuff. So I'm going to take a moment to do that, and I'm going to pause it so I can write it all out so you don't have to watch me writing the whole time. Okay, so I kept going with put my pen down. So I kept going with this. I want to find out, well, as x approaches 1, what is u doing? And so you think about this expression here, as x gets closer and closer to 1, you can see that the u is getting closer and closer to 0. If x was 1.01, u would be 0.01. So therefore, u is approaching 0 as x is approaching 1. And then the denominator, I've got 3 times x minus 1 times x plus 1. So I said, okay, that's 3, and that's u. I got that. And now I just need to know what x plus 1 is. And so I just looked over here and I said, well, if x minus 1 is u, I could just add 2 to both sides over here. And so I have x plus 1. Now I know it. Now I have that on one side. So what would I have on the other side? I'd have u plus 2. And the cool thing is bite-sized chunks works great right now. You could pause it and try it yourself. Just make sure you can do your bite-sized chunks. But it's going to be limit as u approaches 0 of sine u over u times 1/3 times 1 over u plus 2. And so this is 1, and this is 1/3, and this is going to get closer and closer to 1/2. So it's 1/3 times 1/2, which is 1/6. Make my handwriting clear and box it. So yeah, it gets closer and closer to 1/6. So I wanted to show this one because I want to show substitution and show how if you can use substitution to change your variable, but then you have to change it everywhere it shows up. That's a real like sneak preview for stuff later. So the problems like this are going to be very similar. We're going to have problems just like it later on. Okay, and finally, we've got this one. Now you've probably seen this for a while. So you've seen when we had the limit of sine of 3x over 2x, the limit was 3/2. We saw that one earlier. And sine of 2x over x, the limit was 2. And sine x over 2x, the limit was 1/2. And so you might be going, I kind of know what's going on here with these things. And so we want to kind of summarize all that. So it's like, okay, so sine of ax over bx. How am I going to do, how am I going to do this thing? Now you could do it with a substitution. You could make like u equal to ax, and that would work great. Or you could try to do some algebra to work it out, to figure this one out. So you could try to do some kind of algebra to get it into like bite-sized chunks. The problem is with that ax, it's kind of tricky, that'd be kind of awkward. So you can try a substitution, or you can try to do the limit or you can try to do some algebra. I'm going to pause it and write out my answer, and then give you a chance. So you should pause it and give it a try too. Okay, I didn't do substitution. I did sneaky algebra. And so what I did was I decided, okay, I've got sine ax over here. I'd love to have an ax down there. And so I just made it ax and say I have an ax down there. And so as x goes to 0, then these two things are going to be the same. And so that's going to go to 1. And then I thought about, well, what do I need to do to sort of counteract that, to balance out the fact that I just turned that into ax, because I can't just suddenly change it. And so what I thought was, well, if I put an a in the numerator, then those a's would cancel out, and that would just leave me bx in the denominator, which is what I started with. So this is kind of a sneaky little way to do the algebra to make it look the way I want to. We'll also see more of this over the course of the year. So you can see I'm trying to do a lot of sneak previewing. But now as x goes to 0, this thing is just going to go closer and closer to 1, because that numerator, what you're taking the sine of and the denominator are the same, and they're both going to 0. And so we know that limit's 1. And so it's 1 times a over b. And so the answer is a over b. If you did substitution, it's totally cool, because you haven't seen the sneaky algebra thing, but that's fine. And you can see how this fits with what we had earlier, because like in this case, a was 3 and b was 2, so the limit was 3/2. And so the moment you see one, if you see the limit as x approaches 1 of sine of 4x over 3x, then you go, nice try. That's not approaching 0. You can plug 1 in and get an answer, and it's not indeterminate. So it would be sine of 4 divided by 3, whatever that is. I do that every once in a while. I'll make a mistake to see if people are noticing. So it's not to go to you. It's say, are you paying attention? Because you need to make sure you're looking at that. So if you had the limit of sine of 4x over 3x, you can just say it's 4/3, because a is 4 and b is 3. All right, I think that's it for this edition of Limits. I hope you found some things interesting, and also that the things are clear. Please contact me in the usual way to let me know if you have any questions, and have a lovely day. wherever you are and whatever you're doing.